moving on, this is where we are going to wind up with autonomous vehicles in general, and I'm going to be speaking about computer vision. One of the important sensors in a car to enable autonomous vehicles is camera, because it's very hard to, I probably even impossible for a human being to drive with her eyes closed, right? So cameras essentially act as eyes, which will enable the computers to see, identify, and process visual information. It's going to let you process the information, but in a different format, not as like how a human being would do. But essentially, it is based on vision, what you see, and then you process it. And based on the objective, whatever you're training it, whatever you're preparing the computer vision system for, whether it be it an autonomous vehicle, or be it a surveillance system, or be it anything for that matter, the computer vision system can be used based on its objective. And computer vision is different from image processing. As we all know, image processing has been there for a long time, editing pixels and adding special effects, the Snapchat filters that you see, all these come under image processing. But and also the when you take an image, changing the colors and putting settings to it, but computer vision is a lot more than that. Yeah, image processing techniques are used in computer vision, but as a field, it is a mixture of many other domains that enables computer vision to do its task. And it's essentially, and it is very important uh, part of computer vision is artificial intelligence and deeper machine learning, because many of its applications of computer vision is in the field of artificial intelligence. Hence, the technologies from artificial intelligence uh, come in enabling computer vision for its applications. Um, so in this slide, you can see that computer vision is a mix of many other techniques such as artificial intelligence, machine learning, cognitive science. It requires a lot of algorithms to run, and then image processing, of course, and then graphics to enable the computers to process certain information in a particular way based on the objective. It could change. The generic process flow of computer vision, irrespective of the domain, could be put in 5 steps. And these steps are: one, you need to acquire the image. So image acquisition is a process where the computer receives the image in a computer readable format from the sensor, which in this case is a camera, is transmitting the information, and then you receive it, you read it, and then you have different formats of acquiring an image. You acquire the image and then you pre-process the image. We're going to be talking about few methods that can be used to pre-process an image. So it enables the computer to do the other steps that are following, um, to to deliver it better. And we have feature extraction, which is a process where the essential features for that particular applications is extracted by performing few techniques on, or running few algorithms on the pre-processed image. And then detection and segmentation is a very generic and very essential step. You got to be detecting what you wanted to detect, and then you can segment an image into multiple parts and process them individually, or you want to know more about what do you see in each of the regions of the image. So that is another thing. And then high level processing is the last step, where when you have everything and you need to make certain decisions, you need to classify, you need to make decisions as to, okay, now I have this, what next. That Many of the, depending on application, this high level processing can be anything. So uh, like in the case of something like an autonomous vehicle, a high level processing could be something like, okay, the decision that we were talking about, how do we switch the lane, and understanding, and more like an environmental perception, and enabling the vehicle to make the decision. To start with, in pre-processing, a pre-processing is a step, to put it in a nutshell, you can say that it is a method to enhance the quality of image to facilitate other processes. A few of the pre-processing methods that we see here listed are contrast enhancement, noise reduction, image resizing. So technique like contrast enhancement is something like when you view a image, so what you see here is an image with the kid standing there. But then when a computer sees it, the computer is just going to see a matrix of numbers, right? And whatever you see here is the numbers represented as colors, and that's how we perceive it. I mean, that's how we see it. And for a computer, it's all numbers. So a technique like contrast enhancement is going to make one number starkly different from the other for it to process in the next steps better, apply the algorithms better, and for the algorithms to work efficiently. Noise reduction, we don't need certain features that there's certain noise. So at the end of the day, camera is a sensor which is passing electrical signals, and then it is electrical signals and sensors are prone to noise. We do not want noise, and so where we have to be using algorithms that can reduce the noise. Image resizing is another technique which is required for many applications. So these there are a lot more pre-processing steps. In the interest of time and space, I put in these three methods so that you have an idea of what pre-processing methods could be. Feature extraction is an important step because based on the application and based on what you are interested in, the features that you would be interested in could vary a lot. So here in this case, a car, we see the image of a car where, and then we just see the lines and shapes and the edges in that image extracted out. And there are methods to do this particular method to achieve this result, the result that you see in the second picture. So examples of features could be lines, edges, and shapes. All these things make the features. And then uh, in an application, as I had mentioned before, it the features that you would be interested in is going to be very much dependent on the application. The third step would be detection, and for which is followed by high level processing. Detection is made from the features extracted. The features that you extract is going to enable the detection process, and there are multiple detection methods. For example, when you want to detect phase in an image, you would be interested in features that predominantly define which the face, like something that is very particular to the face. So you have, say for example, imagine yourself taking a passport size photograph and you have a white screen against uh, behind you as a background, and the foreground is your face and the background is a white screen. And it is very clear that a white screen is just going to be white, like there is no change in the pixel. And then there are certain features that just gives out that it is a human face. So those features would be of interest. And selection of area of interest, you could have multiple uh, areas in an image, but certain areas could be of more importance to us than the other. For example, in the image that we saw in for the vehicle to shift lanes, we saw vehicles coming from the other side. If the camera is seeing that, that information is not as important as the way as the images of vehicles that are in the same lane or in the neighboring lane, in the same direction of the traffic flow. So you got to be know the computer has to know the area of interest and also prioritize them. And segmenting the regions of image is important because at different locations in the image there could be different things and appearing in different sizes. So image segmentation is a necessary method, and is also one of the most used methods in the stage of detection. In the high level processing, you have interpretation, which is like, okay, now I have all these things detected, now what are they, and how is it relevant to me as a machine, or and what am I going to do with them, how do I classify them, and what do I estimate with those detections that were made in the previous step. This is a generic flow, and then this generic flow can change from one application to another. But then, if you were to kind of summarize them and try to pick out the most repeated steps and features that we see in most of the computer vision applications, it could be broadly put into these 5 steps. as we had spoke as we spoke in the initial content page where we were talking about OpenCV. So OpenCV is an open source computer vision and machine learning library. This was created by Intel predominantly to enable computers to enable core people who are into computer vision and provide them with optimized algorithms. You have a code and then the algorithm is already scripted for you, and then that particular algorithm can be used readily by others. You don't have to script an algorithm every time you want to use them. And we will be seeing an example of how one particular algorithm can be used. And it is available in multiple languages. It is available in C++, Python, Java, MATLAB, or Octave. So these are available. It is available as a package, and you can just download them and store them as library, and you can just import them into your coding environment, and then just start coding, calling the functions from OpenCV. It's used quite extensively by many of the developers, computer vision engineers in the industry and also in the research field. And also, yeah, the academia and industry at the same time. So there are close to 18 million plus downloads, and probably it's even increasing as we speak in this webinar. It is compatible with Windows, Linux, Android, and Mac OS, so it's pretty much available in most of the operating systems. Some of the applications could be face detection, lane detection. Then it has got a lot more application than what we uh, see, like than what we can even think about. So OpenCV is extensively used in computer vision. We're going to be seeing an example of lane detection using OpenCV here in this webinar. As you see in this picture you have red lines and then you have the green lines, and yeah, the lanes are marked in green, and the edge lane towards the left end is marked in red. And a computer, let's see how we can use OpenCV to get this information to a computer. So the steps would be, this is one of the methods to do it, and there are many other methods to do the same task of lane detection. So we will be discussing one such method. First step would be to acquire the image, second mask the image thresholding followed by half transform, and then high level processing of what you would be doing for this particular application. Image acquisition is the process of acquiring an image from a camera to a computer and then the computer reading it. So as you see in this picture, the computer reads out this matrix representation is that of RGB, where red, green, and blue are read as three different two-dimensional matrices, and they appear as numbers, and numbers are in turn translated into a visible format which you see on the screen. So OpenCV has a function called IMRead, which reads out the image, and you can specify in which format would you want the image to be read. In this case, the image is being read in the RGB format or the BGR format, which is followed by OpenCV. And image masking is a method here. In this case, you see that the image, we are not really interested in for detecting the lane, the regions such as the sky and these roads and the signboards and the dividers. We are not interested in any of these to detect the lane. So to detect the lane, we are predominantly interested in the lane markings, and so you got to be masking out a majority of the region of the image to just get the lane. And there are multiple ways that you can do it. So here, using an OpenCV function called fill convex poly, it just treats it as a convex polygon, and then it just masks majority of the image out, and it only provides the area of interest. So in this case, in the case of a computer, masking would essentially be converting the values of other areas that are not of interest to 0 or 1 to for it to be therefore it to have a stark difference between the region of interest. The region of interest would have numbers which would be very different from the region that is not of interest. And then image thresholding. So within the region that we took, we don't want everything. We're not interested in the car in the road. We are only interested in the lane markings. So you can use image thresholding. So these lanes, as you see, are white. White is 255. So between 255 to 0, white takes the value of 255. That's the highest value. So you can easily filter out regions that are not of interest by running some kind of an algorithm where you say that, hey, if you come across any pixel value that is less than the value that I'm interested in, convert them into 0 and only keep those pixel values that are higher. So using OpenCV readily has a method called CV2 threshold, which would enable you to achieve this, to threshold them and only have things that are of interest. Thresholding is a very useful procedure when you know what the pixel values of those areas of interest are going to be in the range of, so that you can readily filter the other areas out. Half transform is one of the method that is used to convert uh, uh, convert points into lines, convert points into lines that are connected. So you see here, this particular in this image, when you see them, they feel it looks like they're going to converge at one point, right? And this is more like an illusion, but then that's not the case. As you go ahead in the same road, you're going to see the distance between them is most likely going to be the same. And so half transform enables us to convert these points that don't seem to be connected, to connect them. The scope, I mean, the explanation of half transform is out of the scope of this webinar. But then, if you have time, do give this a read. It's an interesting method which convert not connected lines into one straight line by converting them into from Cartesian coordinate to a polar coordinate space and then populating them. It's a detailed procedure. You can read them. And CV2 OpenCV has a function that can enable you to do this. So if you pass in an image as an argument, when you call this function, it is going to give out such an image with a line laid out on it as a result of it. So it's very useful in that case. And then yeah, after that, you after this particular step, you know exactly where the lines are with respect to your car and how far are they away from each other. So in an example that we had discussed earlier, where you're shifting from one lane to another, this is a very important step to know where the lanes are and where you are in the lane. So this is one of the examples where you can use OpenCV entirely, right from the beginning of image acquisition all the way till the end. Advanced topics in computer vision could be image classification, object detection, tracking, semantic segmentation, instance segmentation, image reconstruction. So there's a lot of things going on in the industry. Yeah, it's a huge topic in itself. You can read them. There are many articles out there, and please do give it a read. Autonomous vehicles is one such simple application, and there are a lot more complex applications. Use cases would be like lane detection, lane keeping, pedestrian detection. As you see in the second image, the computer vision algorithms are even able to pick up the pedestrians' key points in the body and see their movement and track their movement. Object classification and in-cabin monitoring. So this is one of the one of those topics that I'm working on, where we'll be monitoring inside the vehicle what's going on inside the vehicle, and many vehicles are coming up with this. And a few of the features and applications of this particular domain would be driver state monitoring, occupant monitoring, which gives a lot of potential information for the vehicle when it is shifting from manual mode of driving to autonomous mode or for driver takeover. other applications, optical character recognition, many license plates, and all these things are recorded by cameras, and they themselves can read the numbers on the license plate. Machine inspection, parts that roll out of a production plant are inspected for any faults by just the camera looking at the image of the part. So that is one. And safety surveillance, we are very familiar with how it can be used in safety surveillance. And medical imaging, imagine you don't really have to have a doctor to look at your x-ray to see what's wrong with your bone. Imagine you giving the x-rays passed to a computer, and then computer itself is giving out the results as to, okay, here, this is the problem, and probably this is what you should be doing. And in my opinion, the days are not far away from such a thing happening. And sports play analysis, this is a really fun topic. I have a video on this in the next slide. It's like sports play analytics is used predominantly computer vision. And yeah, I would play this video to just see how this play is converted and interpreted by a computer algorithm. And as you see here, the metrics are calculated in real time, where all these metrics and the players are all calculated and shown in real time as the video is playing. So this is a very interesting use of computer vision, and it is a good example of showing the capabilities of computer vision. And such information can also be used to making your FIFA games better, the other versions that are going to come better. Like, say, you would see probably Cristiano Ronaldo scoring a goal in FIFA, which where he would be acting very similar to what he would do in real life after scoring a goal. So such things can be made can be done using computer vision, understanding the body movements and the behavior of player. Yeah, so the learning steps for computer vision would be first understanding the basic imaging techniques, and motion tracking, optical flow analysis, understanding the topic of that, segmentation techniques, fitting approaches, and machine and deep learning algorithms. So this is to try to put those topics in a nutshell. So essentially, you have to be familiar with linear algebra, probability, these mathematical concepts, and then you start with the basic imaging techniques, understanding what an image is, what is the camera seeing, and what do you see on the computer, and understanding geometry, projective geometry, multi-view geometry. So these things would be an essential base for computer vision. And at the end, machine and deep learning algorithms are used because they are very accurate in terms of efficiency, and also they are well developed, and the processors as of today are capable of delivering and capable of running and inferencing such algorithms on them and provide real time results. So you might have a question, as a computer vision engineer, where in which industry do I think I can be used? Any problem that you think can be solved with vision, uh, there is scope for computer vision engineer. So I have listed five here, but the scope is a lot more than that. Automotive, as I had shown in the examples before, a computer vision engineer is required to develop such algorithms for lane detection, lane tracking, uh, object detection, and many others. And then in medical imaging, like reading an X-ray or an MRI scan, uh, robotics, a lot of big robots or even the smallest of robots that we know of use computer vision. Social media, of course, computer vision is extensively used in social media. Say, Facebook face tagging is one of the applications of computer vision. Like, you upload an image, and then it detects your faces, and then it knows where you are in the image, and then it knows your friend's face, asking you if you want to tag. Yeah, so those things are an example of computer vision algorithm running. And then agriculture, this is a booming field where computer vision engineering is extensively used uh, to to cultivate, to harvest, and many other process where computer vision can be used. So that brings to an end of this webinar